Hi everybody. One of the key concepts in all of physics is the idea of force. Now we use the word force all the time in common everyday English, and the way we use it, at least in physical reality, is about what it means in physics. At least in elementary physics, it means a push or a pull on something. Okay, something that makes an object's motion change in some way, although the object might pull or push back also. In fact, it will. We'll learn that later. It turns out that we can classify forces as either contact forces or field forces, at least here in the big world, what we call the macroscopic world. Contact force would be something that involves, well, contact, direct contact between objects. So for example, this guy who is pulling a rope that's attached to a block that's dragging across the floor, he's exerting a contact force on the rope. The rope's exerting a contact force on the block, and the floor is exerting friction on the block in the other direction, which is also a contact force. Kind of interesting. So what do we mean by a field force? Well, if you think about an apple falling out of a tree towards the earth is pulling the apple down, but it's not in any contact with the apple, at least not until the apple reaches the surface. And so that's a field force. It's sort of magical in a way because it happens without any direct contact, at least visible contact, between the two objects. Now, a different way of classifying forces has to do with what are called the four fundamental forces of nature. The fundamental forces can be classified as follows. First, there's the gravitational force. Think of the apple falling, okay? But it's the idea that all objects with mass are attracted toward each other. So apples are attracted toward the earth, you're attracted toward the earth, but also the moon's attracted toward the earth, and the earth is attracted toward the sun, and hydrogen atoms are attracted toward each other, although with a very, very tiny force, and it would take a long, long time to notice any effect. A second fundamental force that we're all familiar with all the time is called the electromagnetic force. Now this has to do with how magnets work, but it also has to do with electrical forces between charged things like electrons and protons and stuff like that. I'm sure you're familiar with the concept that like charges repel each other. So for example, if I have two negative charges, they would tend to repel each other, right? And opposite charges attract each other, like a positive charge and a negative charge. These are both aspects of the electromagnetic force. A third force that you might be less familiar with is called the strong nuclear force. If you think about the nucleus of an atom, it contains protons and neutrons, right? Shouldn't those protons repel each other? And if the protons repel each other and the neutrons don't do anything because they're neutral, then shouldn't atomic nuclei not exist because they'd blow apart? Well, the strong force is well named because within very tiny ranges, about the size of the nucleus of an atom, it's even stronger than the electromagnetic repulsion, and it affects both neutrons and protons. So that's why an atomic nucleus can hold itself together, because they are attracted to each other with a force that's even stronger than their electromagnetic repulsion. Interestingly, if you cause the nucleus to distort in some way, it could actually split apart. You've heard of splitting the atom, atomic power, nuclear power. That's where that comes from. And I said there were four of them. The fourth one is called the weak nuclear force. Why? Because physicists are incredibly creative when it comes to naming things. It's just weaker than the strong nuclear force. And the weak nuclear force is involved in things like radioactive decay, where a nucleus of an atom, for example, or a neutron itself can shoot out an electron, that kind of stuff that you learned about in chemistry class. So those are our four fundamental forces. They are all, as it turns out, field forces. So where do the contact forces come from? Well, I mentioned that contact forces happen in the macroscopic world. At the atomic level, or at least the molecular level and below, all the forces are actually field forces. You just can't tell because we can't see things at that small level. Think of it this way. If you're sitting on a chair right now, your rear end is composed of atoms, and those atoms are surrounded by electrons, all of which have negative charges. But the same thing is true of the top surface of your chair. It's surrounded by electrons as well. And electrons repel each other. which means your rear end is being repelled by your chair. You're not actually in physical contact with it at the very tiniest molecular level. You're hovering above your chair. That's weird. Here's what's even weirder. Your body is made of atoms. Those atoms are interacting with each other in such a way that they're being held together by these forces, but they're field forces. The atoms of your body are not touching each other. You're just tremendous numbers of atoms that are in close formation that are moving in a very organized pattern. Now when I say you are, I mean your body. This does not include those other more spiritual aspects of yourself, but the material part of you, atoms, field forces. It's amazing. But here at the big level where we are, we're going to talk about things like contact forces. All right. Mass. Well, mass is something that reacts to force in the following way. It's the resistance to acceleration, that is to a change in its state of motion, of an object that's experiencing force. If you push on something, if it has a lot of mass, it resists that push. It's also called inertia. Okay, the resistance to change. So for example, something as heavy as a truck would require a lot of force to cause it to change its motion from not moving to moving. On the other hand, if something's light as a feather, it takes very little force to affect it. In this case, the wind can affect it. The wind's not going to affect that truck very much unless it's a mighty big wind. The bigger the mass is, the more it resists a force. Got that? Now that doesn't have to happen here on Earth. This can happen out in space also. If you think of an astronaut, maybe in the International Space Station doing a spacewalk outside of it, if they get angry and push against the space station, they're not really going to change its motion much because it's huge. In fact, they're going to push themselves away from it because they're the object with the smaller amount of mass. Make sense? Okay. Now, Isaac Newton, that's him. He developed what are called his 3 laws of motion. He also did a lot of other stuff. Newton was into optics. He's the one who discovered that white light can be broken into various colors and that those colors of the rainbow can be recombined into white light. He also discovered the laws of gravity. And while he was at it, just for good measure, he discovered calculus. Pretty smart guy. But the 3 laws of motion that he developed are the ones we're going to talk about today. Well, 2 of the 3. His first one says that in the absence of external forces, the velocity of an object doesn't change. In other words, whatever the object's doing, it's going to keep doing unless some external force affects it. Okay? So if it's moving in a straight line at a constant velocity and there's no force, it'll just keep doing that. Now that's not our common everyday experience, but that's because we live in a world of friction. If you roll a ball, it will slow down and stop, but that's because of friction. If there were no friction, either with the air or the carpet or the floor or whatever, it would just keep on going until it ran into something, which would cause an external force on it. Make sense? Mathematically, the way we write that is, we write that the sum of the forces of an object is 0. Ooh, what's that little funny arrow above the F? Force. Must be a vector. We'll discuss that in a moment. When the sum of the forces on an object, that's what the sigma means, sum of, is 0, then that implies that the acceleration is 0. It doesn't mean that it's not moving. It means that it's not accelerating. Its state of motion is not changing. Got that? Okay, let's talk about that vector thing for a moment. It should make pretty good sense. If you push an object this way with a certain amount of force, and someone else pushes the object this way with a certain amount of force, even if those 2 forces are the same, does it make sense that they would have different effects on the object? Yeah, of course it does. So the direction of force matters, and when the direction matters, that means the thing's a vector. So we're talking about vectors here. The law of inertia, that's what this first law can also be called, was actually first developed by Galileo, but Newton wrote it down as his first law of motion because he extended way beyond what Galileo had said. The second law of motion, again by Newton, says that the acceleration of an object varies directly with the net force and inversely with its mass. Huh? Well, that means when you're looking at an object that's accelerating, if you put more force on it, you'll get more acceleration. That makes pretty good sense. On the other hand, if the object has bigger mass, it'll have less acceleration. I guess that makes sense too. Okay, so this is perfectly reasonable, and Newton came up with it hundreds of years ago. And that's the form in which we usually see it, that the sum of the forces is equal to mass times acceleration, the famous F equals ma. But it really is the sum of the force vectors equals mass times the acceleration vector. Don't forget that mass is a scalar. Now, what this means is, in the x direction, the sum of the forces is equal to the mass times the acceleration in the x direction, and the sum of the forces in the y direction is equal to mass times the acceleration in the y direction. Pretty cool, huh? Let's take a look at these units for just a moment. In the units we typically use, mass is in kilograms. It doesn't have to be. I'm just going to make it that for now. And acceleration, do you remember what unit acceleration is typically in? That's right, it's in meters per second, or meters per second squared. And so if we combine those, we have a kilogram meter per second squared. That has been given its own name. That is called the Newton. See if you can figure out who it's named after. Oh, yeah, okay, that's obvious. And usually we just use a capital N to represent newtons. 1 Newton is 1 kilogram meter per second squared. That is, a Newton of force will cause 1 kilogram to accelerate at 1 meter per second squared. Got that? By the way, if you want to know what that feels like, a Newton, ironically, is about the same force as the weight of a medium-sized apple. Okay, there are about 5 newtons, 4 or 5 newtons in a pound. Make sense? Okay, so you have a feel for it now. Another way of organizing these equations would be to solve for acceleration like the original statement says. And it says that acceleration varies directly with the sum of the forces and inversely with the mass. Okay, and so a Newton per kilogram is the same as a meter per second squared, right? In fact, we could even use this to define a unit of mass. If I solve this for mass, I could have the mass is equal to the magnitude of the force. I'm going to drop the vector symbol, divided by the magnitude of the acceleration. And so if this is in newtons and this is in meters per second squared, this will be in kilograms. Interestingly, if we use the units that we use here in America still, the British units, if the force is measured in pounds, and a pound, by the way, is in fact a unit of force, not a unit of mass. Here's how you can know that. Your bathroom scale measures in pounds, right? If you put the bathroom scale on the wall and then pushed on it with your hand, it would register, wouldn't it? And it's not registering the mass of your hand, it's measuring the amount of force you're pushing with. So force can be measured in pounds. If acceleration, still in British units, are measured in feet per second squared, then you get a very strange little unit of mass. Yeah, an actual unit of mass, and it's called, and I'm not kidding, this is not a joke, it is in fact called a slug. You know, like a slug of lead, that kind of thing. So that actually is a unit of mass, the slug. And it's the amount of mass that will be accelerated by 1 foot per second squared when 1 pound of force is exerted on it. Okay? And by the way, a slug here on the surface of the earth weighs about 32 pounds, about 32.2 pounds. That number might sound familiar to you. Oh wait, that's the acceleration of gravity in feet per second squared, isn't it? Uh-huh, that's right. So let's take a look at some units of various things here then. Mass can be measured in the kilogram in the System International, the International System of Units, or it could also be measured in grams if we're in what's called the CGS system. That means centimeter, grams, seconds. But as we just found out, the mass can also be measured in terms of slugs. Okay? Force can be measured in newtons in the SI system. It could be measured in dynes. A dyne would be a gram times centimeter per second squared. And if you think about that, a gram is 1/1000th of a kilogram, and a centimeter is 1/100th of a meter. So a dyne is very small. It's about 1/100,000th of a newton. It's about the force of a mosquito landing on your arm. You probably can't even feel it. Or in the British system, we could measure force in pounds. By the way, a kilogram, if you're not too familiar with it, here on Earth would feel like it weighs around 2¼ pounds. Okay. A newton causes a kilogram to accelerate at 1 meter per second squared. Okay. That much force will cause that much mass to accelerate at that rate. Okay. And as we said, the newton is the kilogram meter per second squared. If you see kilograms and meters and seconds, then your force will be measured in newtons. Got that? On the other hand, a pound will cause a slug to accelerate at 1 foot per second squared, as we just discussed. So that means that, let's see, a 1 foot per second squared is less than a meter per second squared. A pound is much more than a newton. So a slug of mass has to be a lot more than a kilogram of mass. And as I said, a kilogram is about 2¼ pounds here on Earth, and a slug's about 32 pounds here on Earth. So sure enough, things fit together the way they do. Now I'm going to stop it at this point. In the next video, maybe part 2 of this on force, we'll actually work some problems using Newton's second law. Okay? I'll see you then.